Welcome to Navakokan Education Society's DBJ College, Chiplun. The online session conducted by Shriram Dandekar. My phone number is 9420050909. The same is WhatsApp number. You can ask your doubts on that. We are studying Mathematics Part 2. We are going to start today the second lesson, Applications of Derivatives. In this lesson, we are going to study applications of derivatives to tangents and normals. Then derivatives at rate measure, approximations, Rolle's theorem, Lagrange's theorem, increasing and decreasing functions, maxima and minima. Let us begin our study with applications of derivatives to tangents and normal. In this lesson, we will study only tangents and normals. First of all, let us establish the relation between derivative and geometry. For that, I have considered one graph. You know that for every graph, by plotting the points x, fx, we get its graph. Similarly, here one graph is drawn, y is equal to fx, by plotting the points x, fx. Somewhere there is a point A on x-axis. Corresponding to this A, there is a point on the graph, and that point is P, A, FA. Consider another point on the x-axis, A plus H. The small change in A, it is A plus H. Corresponding to this A plus H, there is a point Q, A plus H, f of A plus H on the graph. Now consider the secant PQ. This is secant PQ. It is the line intersecting in any 2 points of the graph. Now this secant PQ, it has slope. For that, I am going to use the formula of slope y2 minus y1 upon x2 minus x1. y2 is f of a plus h, therefore the slope of secant PQ is f of a plus h minus fa divided by h. Now suppose this h tends to 0. Then as h tends to 0, this a plus h will approach to a. The distance between a and a plus h will become smaller and smaller, and this a plus h will move towards the point A on x-axis. Correspondingly, this point Q on the graph, as h moves towards A, this point Q moves towards the point P, but along the path of this graph. So this secant has new positions like this. This is the first position, then the second position, and gradually it will come here. Afterwards, it will become tangent at point P. This point P, it becomes tangent at point P when in the limiting position, that is when this h tends to A or when this point Q tends to point P. Suppose we make this h smaller and smaller, that means h tends to 0. Then in that case, limit q tending to P, slope of secant PQ becomes the slope of tangent at point P, and therefore the slope of tangent at point P is equal to limit h tending to 0 f of a plus h minus fa divided by h. But using definition of the derivative, we know that this is f dash a, that is derivative of fx evaluated at x equal to a. Let us write the formula for equation of tangent and equation of normal. Suppose y equal to fx is a continuous function of x. I hope you understand better why the function should be continuous. Otherwise, existence of tangent will be in question. Then derivative dy by dx evaluated at x1 y1, that is f dash x evaluated at x1 y1, represents the slope of tangent to the curve at point p x1 y1. Now if we know slope of line and if we know any point on the line, then using slope point form its equation can be found out. The slope point form is y minus y1 is equal to slope into x minus x1. So y minus y1 is equal to slope into x minus x1. So equation of tangent at pxy1 is y minus y1 is equal to dy by dx at x1 y1, or you may write f dash a at x1 y1, f dash a into x minus x1, where f dash a is derivative evaluated at x equal to a or evaluated at x1 is equal to a. This slope is also called as gradient. Please remember this word, gradient. Now let us see normal. The normal is perpendicular line to the tangent, and therefore we know that the product of perpendicular lines is minus 1. So slope of normal is minus 1 upon slope of tangent. Slope of normal at point P is minus 1. Let me write this minus over here. Minus 1 upon dy by dx at x1 y1. Provided that this dy by dx at x1 y1 is non-zero. And therefore equation of normal at px1 y1 is given by y minus y1 is equal to minus 1 upon dy by dx at x1 y1 into x minus x1. Let us solve some problems related to tangents and normals. The first problem I have taken is find the equation of tangent and normal to the curve y equal to x raised to 4 minus 6x cube plus 13x square minus 10x plus 5 at point 1, 3. We have just seen the equation of tangent at px1 y1 is y minus y1 is equal to dy by dx at x1 y1 into x minus x1. And therefore to obtain the equation of tangent, I need dy by dx at x1 y1. Also we have seen equation of normal at point px1 y1 is y minus y1 is equal to minus 1 upon dy by dx at x1 y1 into x minus x1. So here again I want this dy by dx at x1 y1. Therefore I must have the dy by dx initially. So differentiating this y, we get derivative of x raised to 4, 4x cube minus 18x square plus 26x minus 10. Therefore dy by dx at this point 1, 3, putting x is equal to 1, we get 4 into 1 cube minus 18 into 1 square plus 26 into 1 minus 10. It is equal to 2. After finding this dy by dx, let us use the formula. The equation of tangent is y minus y1 is equal to slope into x minus x1. Slope is 2. So y minus y1, that is 3. Y minus 3 is equal to 2 into x minus 1. Rewriting this equation in neat form, we get 2x minus y plus 1 is equal to 0. And the equation of normal is y minus y1 is equal to minus 1 upon dy by dx into x minus x1. dy by dx is 2. Therefore, the equation of normal is y minus 3 equal to minus 1 upon 2 into x minus 1. Again, rewriting this equation in neat form, we get the equation of normal x plus 2y minus 7 is equal to 0. Equation of normal and equation of tangent. 2x minus y plus 1 equal to 0. The second problem we are going to solve is determine the points on the curve 2y is equal to 3 minus x square at which the tangent is parallel to the line x plus y equal to 0. Now we want the points on the curve where the tangent is parallel to this line. Now one line is given to us, that means slope of this line is known. Slope of this line is minus 1. Minus coefficient of x upon coefficient of y, that gives me slope of this line equal to minus 1. Now since slope is equal to minus 1, that slope is equal to dy by dx at the required point. We are going to assume that required point is equal to x1 y1. So dy by dx is equal to minus 1. Now again find dy by dx using this curve, equation of curve, and then compare these two and you will get the value of x, and then sequentially you will get the value of y. Let us solve this problem. Suppose the required point is x1 y1. The line is x plus y equal to 0, that means y equal to minus x. Slope of this line is minus 1 and this minus 1 is equal to dy by dx. So directly I am writing dy by dx is equal to minus 1. Now take this equation of curve. Take this equation of curve 2y is equal to 3 minus x square. Differentiate this. 2 dy by dx is equal to 3 derivative 0 minus x square derivative is minus 2x. This implies that dy by dx is equal to minus x. And therefore dy by dx at point x1 y1 is minus x1. Now dy by dx is minus 1 and dy by dx is minus x1. Therefore x1 is equal to 1. x1 is equal to 1. Put it here. x1 y1 lies on the curve 2y equal to 3 minus x square. And therefore 2y1 is equal to 3 minus x1 square, and therefore putting x1 is equal to 1 in this equation, we get y1 is equal to 3 minus 1 square divided by this 2. Solving, we get it is equal to 1. And therefore the required point of contact is x equal to 1 and y equal to 1, that is point is 1 1. Let us solve the next problem. I hope you understand this better. For the next problem, find coordinates of the points on the curve y equal to x square plus 3x plus 4, the tangents at which pass through the origin. This problem is similar to the previous problem. The only difference is that In that case, a line parallel to the tangent was given, but in this case the tangent passing through some particular point is given to us. This is the variation over here. The process is almost similar. Assume, since we want coordinates of the point, assume that point to be x1 y1, then find dy by dx at x1 y1, then use this knowledge, the tangent passes through the origin, and then you will get the value of x1 y1 etc. Let us solve this problem. Let the required point be x1 y1. Now y is equal to x square plus 3x plus 4. Differentiate this to get dy by dx is equal to 2x plus 3, and therefore dy by dx at point x1 y1 is equal to 2x1 plus 3, and therefore equation of tangent at point x1 y1 using the formula y minus y1 is equal to slope into x minus x1, we get y minus y1 is equal to 2x1 plus 3 into x minus x1. Now this is a tangent, and this tangent passes through the origin, and therefore put y1 is equal to y is equal to 0 and x equal to 0. Since the tangent passes through the origin, we have minus y1 is equal to minus x1 into 2x1 plus 3, and therefore y1 is equal to 2x1 square plus 3. But this point x1 y1 lies on this curve, and therefore point x1 y1 must satisfy equation of the curve, and therefore we get y1 is equal to x1 square plus 3x1 plus 4. These two equations, left hand sides are y1, the right hand sides are different, therefore comparing their right hand sides we get 2x1 square plus 3x1 is equal to x1 square plus 3x1 plus 4. Solving this we get x1 square is equal to 4, cancelling 3x1 both sides, x1 square is equal to 4, and therefore x1 is equal to plus or minus 2. Now we have to use this and find out the values of y1. Since there are two values for x1, there will be two different values for y1. Let us erase these two lines. Since x1 is equal to 2, that implies y1 is equal to 2 square plus 3 into 2 plus 4, putting it here, and we get corresponding value of y1 is equal to 14. If x1 is equal to minus 2, then y1 is equal to, again putting it here, x is equal to minus 2, we get y1 is equal to 2. And therefore the required points are 2, 14 and minus 2, 2. 2, 14 and minus 2, 2 are the required points. Let us solve one theoretical question that you have already studied in 11th standard. You have directly taken the formula. Show that the equation of tangent to the ellipse x square upon a square plus y square upon b square equal to 1 at point p x1 y1 is x1 upon a square plus y1 upon b square is equal to 1. The procedure is similar. Since we want equation of tangent from the given equation of ellipse, find out dy by dx, then find out dy by dx at this point, and then use the tangent line equation y minus y1 is equal to slope into x minus x1. Let us solve that. The given equation of ellipse is x square by a square plus y square by b square equal to 1. Let us differentiate this with respect to x. 1 by a square is constant, derivative of x square is 2x. 2x upon a square plus again 1 by b square is constant as it is, derivative of y square with respect to x is 2y dy by dx. The right hand side is 1 constant, derivative of 1 is 0. Therefore, from this we get dy by dx is equal to minus b square x upon a square y. You might have solved this problem of obtaining derivative in parametric equations. Dy by dx is found out. Now dy by dx at point p x1 y1. It is equal to minus b square x1 upon a square y1. And therefore equation of tangent is y minus y1 is equal to slope multiplied by x minus x1. Derivative is slope. Multiply both sides by a square y1. We get b square into x into x1 plus a square into y into y1 is equal to b square x1 square plus a square y1 square. Dividing both sides by a square b square, we get x1 upon a square plus y1 upon b square is equal to x1 square upon a square plus y1 square upon b square. Now remember that this point x1 y1 lies on this ellipse x square by a square plus y square by b square equal to 1, and therefore this point must satisfy this equation x1 square upon a square plus y1 square upon b square is equal to 1, and therefore this right hand side becomes 1, and we have the proof. Since x1 y1 lies on this, we have x1 square by a square plus y1 square by b square equal to 1. Putting it here, we get x1 upon a square plus y1 upon b square is equal to 1. Here ends this theoretical question. This is equation of tangent to the ellipse. Similarly, you can try for equation of tangent to circle, equation of tangent to hyperbola, equation of tangent to parabola on the similar lines. Try yourself. Suppose the curve given us is in parametric form. Then let us see how to find out its equation of tangent and equation of normal. One problem I have chosen for you. Find equations of tangent and normal at point T on the curve x is equal to a sin cube t, y is equal to b cos cube t. To find equation of tangent, we need dy by dx. Since x is function of t, y is function of t, I can find dy by dt, dx by dt. Using that, we can find dy by dx, and then at point T we want, so dy by dt at point T can be find out. Let us solve this problem. X is given a sin cube t, therefore dx by dt using chain rule 3a sin square t into derivative of sin t is cos t. Y is equal to b cos cube t. Its derivative with respect to t, dy by dt is equal to 3b cos square t into derivative of cos t is minus sin t. Therefore dy by dt is minus 3b cos square t into sin t. And therefore dy by dx is dy by dt upon dx by dt. Writing these two values, cancelling the common factors, we get dy by dx is equal to minus b cos t upon a sin t. The equation of tangent at point T is, now at point T I must have the value of x1, value of y1. Value of x1 is a sin cube t and value of y1 is b cos cube t. If t in terms of pi by 2, pi by 6, pi by 3 etc. is given, then you can find out the values easily, numerical values. For example, if t is equal to pi by 2, then x is equal to a sin cube pi by 2. Sin pi by 2 value is 1, therefore it will become a only, and y is equal to b cos cube pi by 2. Cos pi by 2 is 0, therefore y becomes 0, and so on. But we want the generalization, so we are keeping t as it is, and therefore y minus y1, that is b cos cube t, is equal to slope into x minus x1, that is a sin cube t dt. Now rearranging the terms, we get ay sin t plus bx cos t is equal to ab sin t plus cos t. AB sin t into cos t, and therefore x upon a sin t plus y upon b cos t is equal to 1. Dividing both sides by this term, we get this, and this is equation of tangent at point t. Now since this is slope of tangent, slope of normal is reciprocal of this. Using that reciprocal slope, we can find, using similar formula, equation of normal. Equation of normal is y minus y1 is equal to slope into x minus x1. Again, rearranging the terms clearly, we get equation of normal as ax sin t minus by cos t is equal to a square sin raised to 4t minus b square cos raised to 4t. Equation of normal. Let us solve slightly difficult problem. Tangents are drawn from origin to the curve y equal to sin x. Prove that their points of contact lie on the curve x square y square equal to x square minus y square. Now tangents are drawn from origin to this curve. So this curve is given to us. First of all, differentiate this and find dy by dx. Assume that the point of contact on this curve y equal to sin x is x1 y1. Therefore, since y is equal to sin x, therefore dy by dx is equal to cos x, and therefore dy by dx at x1 y1 is cos of x1. The equation of tangent at point x1 y1 is y minus y1 upon x minus x1 is equal to slope dy by dx. So y minus y1 upon x minus x1 is cos x1. This is equation of tangent. Now here this tangent passes through the origin, and therefore put y and x both equal to 0. So putting x and y both equal to 0, we get minus y1 upon minus x1 is equal to cos of x1, and therefore y1 upon x1 is equal to cos of x1. Let us term this as number 1. This point x1 y1, it lies on the curve y1 is equal to sin x. Y is equal to sin x. Therefore this point must satisfy this equation, and we get y1 is equal to sin of x1. y1 is equal to sin of x1. Now call this as equation number 2. Now in equation 1 we have the value of cos x1, in second equation we have sin x1. Since we have sine and cos, we can square and add to get 1. The first fundamental identity, sin square theta plus cos square theta is equal to 1. Using that, squaring and adding both these two, y1 square upon x1 square plus y1 square is equal to 1. Multiply both sides by x1 square, we get y1 square plus x1 square y1 square is equal to x1 square. Now take this y1 square on the right hand side, therefore we get x1 square y1 square is equal to x1 square minus y1 square, and therefore the point x1 y1 satisfies the equation x square plus y square equal to x square minus y square, and therefore it is clear that this point x1 y1 lies on the curve x square y square equal to x square minus y square. Hence the proof. That's all for today. In the next lecture we will study the derivative as rate measure. Till that, bye bye. Please ask your difficulties on WhatsApp, and also like this video if you really like this. Otherwise, give your comments to improve this video. Thank you very much.